This is our second to the last subtopic for our topic 1, so the cost-driven design optimization. So engineers must maintain a life cycle viewpoint as they design products, processes, and services. Such a complete perspective ensures that engineers consider initial investment costs, operation and maintenance expenses, and other annual expenses in later years. So, nasa like contingency daan and environmental and social consequences over the life of their designs. So in fact, a movement called Design for the Environment or DFE or green engineering has prevention of waste, improved material selection and reuse, and recycling of resources among its goals. I think we are all familiar na with this. It's just that wala ako, personally, I am not aware na mao din na siya ang term na design, sila ang more advocate nga movement. But if you noticed, when we go to some grocery stores ka ng mga eco bag, we replace before katong mga plastic bags, we replace them with eco bags or we bring our own kanang sudlanan. So I think that's one of the kanang mga product nila. Ingana. So designing for energy conservation, for example, is a subset of green engineering. Another example is the design of an automobile bumper na pwede easily lang ma-recycle. So as you can see, engineering design is an economically driven art. So I also noticed or kanang nakita po na ako sa kanang mga Facebook posts na there are mga kanang food containers na made of sugar tubo or sugar canes ingana or unsa pato na other materials, so which is kanang environment friendly. Also we have the kanang what we call the shampoo conditioner bar na ginarap lang sa murag Japanese paper or something paper. So when it is being delivered to your house, you just have to unwrap it and wala siya kanang plastic nga kanang wrapper na. So to help the environment ingana. So I think this is what the movement is for. Okay, and for you to have a better kanang understanding of what this movement is all about, let's watch this video.
Welcome back. So today we're going to talk about the design for environment, or DFE. And it's a different way of thinking about design because we don't want to look at design as just this process in which we just make products and then we forget about it. Actually, products have what we call a lifetime or a life cycle. And that's something that we're going to get into, is what happens not only when our customer uses our product, but what happens when they're done using the product. So this is where design for the environment comes in. So first of all, let's look at some example products where the design for the environment or DFE principles have been applied and they've been embodied. So let's take a look at some examples in the last few decades. So one, Patagonia. They're a great example of a successful clothing company that has really taken this to heart. So if you consider, in 1993, they became one of the first companies to use post-consumer recycled materials in their products. And if you've ever worn any of their products, you wouldn't really notice it. It doesn't seem like you're compromising on quality or anything like that. Most of their garments contain at least 54% recycled polyester, and they are 100% recyclable through their take-back system. So they'll actually take back their products and be able to recycle and reuse the materials into new products. So that's one example. Another good example, and you probably have never heard of this, it's called the Stokey chair, the Trip Trap chair. So it's basically a chair, and it was way back in 1972, they decided, okay, well, what if we just have a chair that as a child grows, that they can still use the same chair with just some adjustments. And so that's essentially what this is. You can see how it can be an infant chair, a toddler, a kid's chair, all the way to a young adult. And so in that sense, they don't have to keep buying new types of chairs or get rid of a infant or kid's chair once it's done. Another example is the Dunlop recycled Wellington boot. These are actually very high quality boots, and they're great for water resistance. They're made from polyurethane, PVC, and rubber. They developed these as a line of recyclable boots. So not only can they take back these boots, but then they can then be reground, and then they can remanufacture completely, almost 100% back into new boots again. So that's pretty dramatic when you think of the functionality of what you get out of it. So if you have to go tromping around in the rain all the time, great, you can buy a pair. Hey, they wear out, they break down, you're done with them. You send them back to Wellington, they will make a brand new pair out of the pair that you had. And finally, another example is called the Freetag bags. They use, interestingly enough, truck tarps, inner tubes, and seat belts to make a whole different line of bags, carrying bags. And you can kind of see, as they show in this picture, where they kind of show where it was taken out of a tarp. And so it still has a designer look to it and a functionality, but they make some pretty strong residual bags. Again, so there's a lot of recycling and reuse of materials in all these different examples. What we're really trying to get at, the problem, is the environmental impact by not doing things like this. So as we know, global warming is a major issue. If you think there's an argument on that, not only do thousands of scientists all agree that it's a huge issue, but all of the trends are showing that as well if you actually look at the data. It's not an opinion, it's not a political point of view, it's a fact. So global warming, when you're looking into it, is a deep issue and a problem that is getting worse and worse unless we are doing something about it. And that has to do with a lot of emissions in manufacturing, emissions in energy production, all sorts of things. Another environmental impact is, we're on this one planet and we're depleting resources. When you look at the biomass of human beings, we've gone from, being thousands all of a sudden to almost 8 billion across the world. And when that happens, we're having a dramatic effect on all these types of systems, on the resources, on the ecosystems, on the diversity of life, all these types of things. And projected in the future, as long as our population keeps growing, we're going to have even more dramatic effects. So we have to start addressing these issues now. Solid waste, major issue. Water pollution goes along with air pollution, and also the degradation of land, where we used to be able to have crops and, again, have diversity of life and those types of things. So I've put a whole list of resources on here that you can actually look at, and websites for all these things if you want to get a lot more information on this. And there's tons of research out on all these areas and the actual human impact on all these things. So how do we mitigate this, or how do we, if we can, reverse this in a process? Because we're not going to stop making products. People are still going to have needs, and people are still going to want solutions for those needs. So we have to figure out maybe a smarter way, a smarter solution. So we get to a question: is this a legacy problem, something because all the products in the past have been the way they have and are causing major problems in the environment? Is it a legacy problem? Is it a materials problem? Well, maybe we just need to be using better materials that are recyclable and reusable, are sustainable. Is it just that kind of a problem? Or is it a solvable problem? Some people think you can't do anything about it, so why worry about it? At some point, everything's going to hell in a handbasket. Well, I tend to not be in that boat. I think there's a lot we can do. It just requires a lot of entrepreneurs and engineers, scientists, and people working the problem so that we can come up with a great solution. In fact, it is all of these types of problems. It is legacy, it is materials, and yes, it is solvable. So how do we go about doing that? What we really need to do is we need to consider biointegration of our product systems, because as I'll show you later, there really is no such thing as a way. When we look at products and say, okay, when we're done with that, we'll throw it away. That whole mindset, that thinking that there is somewhere out there that you can put your trash and then it's away, is complete fallacy. It's not true. There is no such thing. it's still in the environment, it's still in the earth. And as far as we know for now, that's all we've got. We haven't been able to take our population to other planets yet. We're working on that. We haven't been able to expand beyond this rock we call Earth. So because of that, we have a closed system. And in a closed system, we got to get smarter. And we got to adapt and work these solutions better. So being able to biointegrate any type of production or any type of designs of whatever we're doing with our products is critical, because we have to understand that there is no real separation between what we make and where we live. They're all interlinked. It's one big complex adaptive system. The other concept is biocompatibility. With the context of the materials that we do choose, we want to make sure that we're using materials that are compatible with life. Why? Because that's what we are. And essentially, if we don't do that, we're slowly killing ourselves, killing other animals, killing plants, those types of things. So that's another component that we have to really consider. So how do we do that in our materials choice and manufacturing? That's what design for environment, or DFE methods, are all about. So it's a way we can minimize and or eliminate these environmental impacts over the product, over its life cycle. And there's lots of interesting research and development, and not even just there, but actually it's already in the commercial space big time in a lot of areas. So effective DFA will practice and maintain a product so that we can improve it not only in the quality, but all the cost, and reduce the environmental impact. That's the ideal. That's what we'd like, is for all of those to be true. It expands in the traditional manufacturer's focus and on the production and distribution of the products. What we want to get is a closed loop life cycle. So what do I mean by that? It means that we're going to be taking away from this throwing away, and then there's an open cycle where we don't care about what happens to our product anymore. And we're going to be bringing that back around and figuring out how to reintegrate. So this is a huge area of innovation. If you're looking for opportunities where entrepreneurs can make a big dent in this, there's a lot of opportunity in this case. In fact, in the news just now is China has decided to up the regulations on the type of recyclable materials that it will accept. So it just stopped taking a whole bunch of our recyclable materials. So we can look at that as a problem. So many cities are saying, okay, well, we're not going to have a recycle program anymore. That's very short-term thinking. The better term thinking is for companies or for places that used to rely on the Chinese companies to do that, say, hey, why don't we make companies in the United States that could take care of that? You know, if we're talking local. Globally, it also opens up the landscape to, there's a lot of other countries that would be willing to create companies to take up all that area, because the demand hasn't gone away. Just because you say, yeah, we don't want to take this anymore, doesn't mean the demand's gone away. It just means that we have to retool it. It also means that we have to get the quality of the recycling and the purity of the materials better. And so there's opportunities in that space too, on how do you separate out the different materials? How do you get to a higher purity of, say, a polyethylene or a polyvinyl chloride or cardboard product? How do we do that? How do you remove food particles from those types of things? All sorts of areas where there's innovations because there's problems that need to be solved, and there's money to be made if you can. So let's talk more about this product life cycle. We've mentioned it a couple times now. Really, I like to refer to the cradle-to-cradle model, and I didn't come up with this model. There's actually a whole non-for-profit group that came up with it, and there's something called cradle-to-cradle certified, and that means if you follow kind of the best practices of this non-for-profit group of organizations that have kind of come together as a consortium, you can get the stamp of being cradle-to-cradle certified. So what it does is it takes our idea of, okay, we're going to produce a product. That's old hat. We know how to do that. We're going to distribute a product. We know how to do that too. And then a customer is going to use our product. Fantastic. Then at what case do we go? Well, what we don't want to have is where they just go to dispose and consider that there's some away out there, which is no such thing. And then that's the end of it. So you can see how that literally looks like an open loop cycle. We need to close that loop to where then disposal then becomes maybe retrieval back into materials that then can go back into production. And that's, again, an ideal case, but it's not the whole story, but it's definitely a step in the right direction. So to consider what the life cycle assessment is, there's a whole area in sustainability research and actually sustainable companies that embellish a whole bunch of time into this. It's called LCA assessment, or life cycle assessment. It quantifies the environmental impact of a product over a period of life cycle. So what are the environmental impacts? Well, it could be energy impact. It could be carbon footprint, and a number of other factors that you can measure. So there's several steps in this analysis. So one is you want to prepare proposed design options. So say you've got a design and you know functionally what you want to do, and then you have different options on maybe materials choices or sourcing where you're getting your materials from. Then you identify the life cycle, including the recycling and disposal components. Identify all the materials and energy sources that are used. Then you identify outputs and waste streams. Then you want to quantify the impacts of each material, energy, and waste stream. And as you can imagine, this gets pretty complicated, and to do it just on the back of the napkin is kind of difficult. I've created some new equations that I've been developing on getting a very simplified form of this. However, you can actually use software to get a more advanced level look at this. Aggregate impact onto the categories for comparison. And then you can make a choice. You can make a more conscious choice based upon your feedback of this information, say which one has the least amount of environmental impact. And if you can get one that's actually an upcycle for the environment, fantastic, which means that actually it's improving the environment. That's a newer way of thinking. It's not how can we minimize bad, how can we actually promote good by what we do from an environmental standpoint. So that's a more modern way of thinking. So it does require specialized LCA software packages and training. It's a bit beyond this course, but there's folks in sustainability that take this quite seriously, and there's actually a lot of commercial software available already. And there's lots of capabilities. So one of the common ones is SEMA Pro. There's Gabby, Open LCA, which is great because there's a huge community around it. As the name implies, it's open LCA software, so you can download it for free, and you can start using it and learning about it. There's tons of tutorial videos on it. So a lot of institutions will start with that before a pay model. Sustainable Minds, etc. So the list is growing. So let's take a look at what you might be looking at with some LCA software. So for example, here's a viewpoint of SEMA Pro. Now, if you notice, we have a whole bunch of comparisons with these bar graphs, so let's kind of break this down. On the x-axis, really what we're looking at is kind of some of the different categories of environmental impacts. So over to the far left, we have carcinogens, we have respiratory organics. This is where you have problems, respective organics and inorganics. What's the climate change factor, radiation, ozone, exotoxicity, yada, 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 all the way to fossil fuels. So this list can be really long. So you really want to focus on what are the big things that you want to make an impact or minimize the impact in. Then they have basically a scale of 100% being the worst, 0 obviously being the best. So in this case, they have, they're looking at comparing energy production and what are the impacts based upon where they go. Do they do a central, kind of a north area, or this other production area called UCTE? So they're really comparing 3 different models of, they want to do something of these 3 electricity networks, and they want to say which one should we choose that's going to minimize the impact. And if we look at them, so let's say we're looking at the central, that's all the red bars. And of the red bars, you can kind of just at a quick glance when you're looking at data like this, we've got 4, 5, 6, 7 that are at 100%. So they're having a dramatic effect on land use, acidification, exotoxicity, climate change, inorganics, organics, carcinogens. So, all right, we get some reference there. If we look at the yellow one, which looks like it's the next as 5 bars that are all 100%, then there's several that are lower than that. And really, if you look at the green, only the green has something that's 100% for land use. Everything else is actually much, much lower. The climate change is specifically much lower. The number of carcinogens is dramatically lower than any of the other options. So that's what you're looking for, is which things have the least amount of environmental impact. So in this case, and it wasn't by accident, they colored it green. The green one wins because it has the least amount of effect compared to the rest of them. And again, this is just one type of software, one type of characterization, comparison. And as you can imagine, there's lots of ways to analyze these things. So you probably would analyze in several different ways, also from cost factor, to figure out what the choice would be for your company or your enterprise. By doing this, we really start embracing the cradle-to-cradle idea. The first book on this was by William McDonough and Michael Braungart. In fact, in the shell, I want to refer you guys to a video to watch. It's actually a brief TED Talk, but an excellent TED Talk by William McDonough, where he talks about this effect, and he's pretty dramatic in the sense of looking at the scale of things and how important this is. So he has an excellent example on not only just designing products, but their firm was actually required to help design cities, entire ecosystems that had to be self-sustaining. So it's really, really a powerful talk. So make sure that you look at that in the shell. I won't do it here. It's about 15, 18 minutes. So the cradle-to-cradle, or C2C, is a DFE method. It emphasizes the renewable resources, sustainable life cycles. Again, these are the authors. If you want to read it yourself, cradle-to-cradle, remaking the way we make things. The newer book is called The Upcycle, and then again, that's more modern, of not just minimizing bad, but actually promoting good, to where we can make products that actually make the environment even better, to where maybe the breakdown of your product actually becomes fertilizer or food for plants. That's actually something that would be considered an upcycle. And they do lots of different types of design work. So their firm, McDonough Braungart Design Chemistry, or MBDC, they work with lots of different companies to help select the safest materials in product design. Probably a little bit easier for larger companies to spend the time and effort in doing this. So it's usually after you've gotten a product and you're trying to optimize and minimize and make more environmentally friendly. A little bit more difficult to do at a startup level because you're so concerned about getting it right and making sure the function's right. However, you could go into it with that design and make that part of your value proposition at the get-go, to say, look, here's a differentiator. Our product makes use, or is fully recyclable, or is this. And then it becomes a selling point, which may be that you can be able to charge a premium for your product versus a competitor's product. So you can take that standpoint, in which case that would be a really interesting use case here. And there's actually several startup companies who have taken that approach. To make a finer point on it, what we really talk about is not just the initial product cycle that we discussed before. So if you notice, again, here we have the same cycle we talked about before: production, distribution, use. But now we've gotten rid of that disposal, because again, that's throwing away. And now that we've seen this, we know there is no such thing as a waste. So everything now has to be focused on recovery. So this is another part of the value chain. In this case, what are our options? Well, recovery could mean we want to then recover as many of the materials that become raw materials so that we can remanufacture and make more product or new products. So that's remanufacturing is one of those areas. Also, recovery could mean reuse. So that's where, okay, maybe we use this product as something that it's no longer valid to use of its initial use for that life, and now it has a second or third life in some other use. That's kind of a little bit lesser way to go about it, but nonetheless, it is a way to not have to throw things away. You can actually extend the life cycle. Another is post-industrial recycling. So maybe we get production and we have some scrap. Maybe those scraps can go right back into our materials. That's already commonly used. Here's the big new way of thinking, and this is something that many manufacturing groups and stuff have not really incorporated yet. So instead of disposal, we want recovery then to be a deposit. If we choose our materials correctly, instead of disposal, we want to deposit different types of things into the natural bio life cycle. Right now, excuse me, disposal is a downside because we're putting toxins, we're putting materials that aren't going to break down for 1,000 years or 10,000 years, depending on what it is. And it's going into landfills and things like that. So we're already depositing this type of stuff into the system, and it's really polluting our wastewater, or actually our water systems, wastes, and all those kinds of things. So the problem is it doesn't feed into this natural bio life cycle well. And in fact, it even disrupts some of the normal parts of the life cycle, such as natural decay, where we get new resources and we can extract those resources. So how do we modify that? Well, we keep the things that we can't put back into the natural biological life cycle, and we keep them in the production industrial life cycle. So what's an example of that? An example of that is something like aluminum. Aluminum takes a lot of energy, has a huge carbon footprint to be able to pull out of the ground and get that aluminum. However, it's not very useful to put it back. It can contaminate water and a whole bunch of other things. Not that it's necessarily a terribly toxic material, but it doesn't actually do anything in the biological life cycle. However, aluminum is extremely recyclable. So the benefit of that is we can keep it in the production industrial life cycle and keep having an aluminum life cycle that keeps going round and round and getting made into new products. It's very easy to keep it in the recycle category, and it's better placed to keep in here and not have it go into any landfills and things like that. And then maybe during the recovery, we decide, okay, only things that are truly organic that can break down into organics get deposited back into the natural life cycle. We do not put toxins in, and we don't put inorganics in, which can then toxify, again, waters and things like that, or keep things from growing. So we want to make sure that we don't put these things into the natural life cycle, because that's what degrades the land, causes a lot of water pollution, air pollution, those types of things. So from a materials choice standpoint, we want to choose materials that don't have resulting toxins, don't have resulting inorganics, and don't go into there. They can get put into another industrial life cycle that could get reused and reused. Or, well, we also want to minimize the amount of those types of materials we want. So we want to take them out of the production cycles altogether and not actually even extract them in the first place. So there's a lot of different ideas there on how to do that, a lot of different research doing that. I'm actually consulting with a company now that's actually looking at being able to taking out mining toxins and do something constructive with them and get them back into the production industrial life cycle and take them out of the environment. Then, if we're only promoting things that do naturally go into the biological life cycle, now they can naturally decay, and then they become resources through the biological cycles, and thus they become renewable resources. The other thing we don't want to do is pull resources too fast and pulling non-renewable resources and depending upon those for our raw materials. So we want to prevent taking more of that out and only use renewable resources when it comes to our material selection. So by doing all these things together, we sync up these two life cycles, and we can keep things running, and then we're not degrading the earth as a whole. So what are some of our conditions for sustainability? To not put a finer point on it, the earth is a closed system. So don't just consider that it's a closed system. It is a closed system with all intents and purposes for life that is on earth. Until we can really break out of our system, start colonizing other planets, we're pretty much stuck here. So it's a closed system in that concept. Now, what does come in here is we have solar input, so we have energy. In fact, there's more than enough solar energy that would cover all of our power needs if we actually just harnessed it. More than coal, more than oil, or anything like that. If you actually do the analysis on it, you don't actually even need to have those in the long term. And also natural biocycles. We have to make sure that we sustain those. So solar energy obviously makes a huge amount of sense because we have the largest energy resource sitting there with the sun. And other renewable fuels are sustainable energy sources. Resource usage must be balanced to the rate that the Earth can regenerate those resources. So remember, the definition of a renewable resource means that you can generate at or better, that's important, at or better, the amount of which you withdraw. Think of it like an interest-bearing account. You don't pull off the principal. If you want something sustainable, you only pull off at the interest or less. So your interest has to be greater than your use. So same thing here. It's not rocket science. It works just like pure finance. You can't extract more than you can replenish at the rate you can replenish. Fossil fuels do not do that at all, period. I mean, it took hundreds of thousands, millions of years to build up the fossil fuels that we've been burning through in 100 years. So that's not a sustainable rate. We can't wait another million, hundreds of millions of years for the next century. That's not going to happen. Toxic waste, heavy metals, radiation, other molecular garbage, we should eliminate it from our production cycles. They're not part of the biocycle, yet we dug it all up out of the ground now to put it in. So we may need to put it all back as much as we can in the ground, unless we can keep it, again, in just the production cycle and prevent it from going into the biocycle.
So for cost-driven design optimization problems, the two main tasks are as follows. First, you have to determine the optimal value for a certain alternative's design variable. For example, what velocity of an aircraft minimizes the total annual costs of owning and operating the aircraft. So you have to determine ang optimal value kung naa kay alternative na design. So the aircraft na kanang velocity is just an example. Then second, the second task, main task, is select the best alternative, each with its own unique value for the design variable. For example, our example here is what insulation thickness is best for a home in Virginia. Is it R11, R19, R30, or R38? So if you are looking for kanang best na insulation thickness sa Virginia, according to Google, Virginia is humid, subtropical. So kung pangitaan nimo siya insulation nga kanang best insulation, if magtukod kag for example balay dito, so you have to um 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 you have to choose well kung unsa sa ilaha nga dili pod, like for example kung mag-choose kag R38, baga na siya kaayo, basin dili ra need na baga kaayo ra, basin in the middle or pinaka nipis will be sufficient na for your home, for the home na imong ikuanan, diba? So yeah, in general, the cost models developed in these problems consist of three types of costs. So there are three types of costs na involved. First is the fixed cost. Second is the cost that vary directly with the design variable. And third is the cost that vary indirectly with the design variable. So a simplified format of a cost model with one design variable is shown through this formula. Okay, so we have here cost is equal to A times X plus B over X plus K, where A, nimo, is the parameter that represents the directly varying cost, and B is the parameter that represents the indirectly varying cost, while K is a parameter na nagrepresent sa imong fixed cost, and X is the design variable in question. Okay, like for example, the weight or pila ang weight, pila ang desired nga weight, pila ang design velocity nimo. So that is being represented by the variable X. In a particular problem, the parameters A, B, and K may actually represent the parameters that we mentioned earlier. These actually represent the sum of a group of costs in that category, and the design variable may be raised to some power for either directly or indirectly varying costs. So the following steps outline a general approach for optimizing a design with respect to cost. So yeah, let's go through this five 5 steps. Okay, so first, identify the design variable that is the primary cost driver. So, either it's a pipe diameter or ang insulation thickness. Ang variable na imong concern, or we call the primary cost driver. So, unsay mas what do you think? Ka mas magastuhan when you think about this design. Nga na. And asa ka mas makatipid, or how unsa nga pwede nimo mabawasan ang diameter ba sa pipe, ang insulation thickness, ang length ba sa imong material, something like that. So write an expression. Second, write an expression for the cost model in terms of the design variable para na uniformity and na a common unit of dali ra siya i-evaluate nimo. Third is set the first derivative of the cost model with respect to the continuous design variable equal to 0. So for discrete design variables, compute the value of the cost model for each discrete value over a selected range of potential values. So we can actually use this one if natay actual and if natay given problem. Okay. Anyway, I am sharing this to you if kanang interested mo to solve something that involves ang cost mag-optimize o design, okay, with respect to cost. And where were we? Number 4 is solve the equation found in step 3, katong equation na makuha nato for the optimum value of the continuous design variable for discrete design variables. The optimum value has the minimum cost value found in step 3. So this method is analogous to taking the first derivative for a continuous design variable and setting it equal to 0 to determine ang optimal value niya. Number 5, the last is for continuous design variables, use the second derivative. So you have to, after sa first, you have to compute or kanang rewrite nimo siya, isolve nimo siya, and get the second derivative of the cost model with respect to the design variable to determine whether the optimal value found in step 4 corresponds to a global maximum or minimum. So, yeah. So, oh, that's the end for this topic. So please watch the video, the supporting video for this one. Thank you.